Stick framing is a time-honored method that involves assembling individual pieces of lumber to form a functional framework. In roof construction, stick framing involves assembling individual pieces of lumber such as rafters, ridge boards or ridge beams and ceiling joists on site to form the roof's framework. Whether it's a simple gable over a farmhouse or a sprawling hip roof wrapping around a custom hillside home, stick framing remains one of the most versatile and adaptable methods of roof construction. It stands in contrast to prefabricated trusses or panelized roof systems, which are manufactured off-site and hoisted into place as complete units. While trusses have become the dominant choice in production housing due to their efficiency in repetitive large-scale builds, stick framing remains a preferred method in both simple and custom roof systems. For straightforward shed roofs or gable roofs on small additions, porches, and garages, stick framing offers unmatched practicality with no lead times or craning logistics while offering complete on-site control. On the other end of the spectrum, in custom homes or remodels where vaulted ceilings, intersecting roof lines, or architectural variation make trusses impractical, stick framing again proves indispensable. Its strength lies not just in its adaptability to complexity, but in its simplicity where simplicity is all that's needed. Historically, stick framing was the norm. Before the advent of engineered trusses in the mid-20th century, nearly every sloped roof in North America was laid out with a framing square and a strong grasp of roof geometry. The system was refined over generations and guided by trade experience and evolving building codes. It was not just carpentry. It was applied structural thinking long before structural engineering became a formally licensed profession. Today, stick framing endures not just for its adaptability, but also for its practicality, especially in smaller builds, remodels, and roof shapes that defy prefabrication. Framers retain the ability to make adjustments on the fly, respond to real-world site conditions, and shape the roof in direct coordination with the structure below. In this video, we'll explore the landscape of stick-framed roofs from the common roof types typically framed on-site to the essential components that make up a stick-framed assembly. We'll examine how these elements work together to form a stable structural system built to provide a defined load path while highlighting the differences between conventional and engineered framing approaches in this domain. Finally, we'll consider the practical and architectural advantages that make stick framing an essential element of today's construction environment. Just like manufactured trusses, stick framing can be applied to a variety of roof geometries. Most assemblies fall into one of three primary types, including shed roofs, gable roofs, or hip roofs. These fundamental roof forms provide a structural and spatial framework that is repeated across much of the stick framing landscape. Let us look at how each of these roof types is framed. The shed roof is the simplest of all stick-framed roof forms. It consists of a single, sloping plane pitched in one direction, with no ridge line or hip rafters. Structurally, it's composed of a series of rafters that span from a high wall, which is the tall bearing wall, to a lower one. Sometimes the plate height of the two opposing walls is similar, requiring the rafters to be cut to provide the required slopes. In this case, the rafters used are larger than the actual required depth to allow for cutting without compromising on the structural integrity. Because of their simplicity, shed roofs are ideal for porches, home additions, modern minimalist architecture, and structures with limited spans. Shed roofs are also commonly used to frame low roofs, which occur typically when a first-story roof is required on a small portion of the structure where the adjacent section is 2 stories tall. In this case, the shed roof rafters are supported by bearing above the wall on the low end and supported by a ledger on the second-story wall. The simplicity of shed roofs makes them framer-friendly with minimal cutting, clear load paths, and fewer connections. For cases where shed roofs are framed above bearing walls, the load path is simple. The rafters transfer vertical loads directly to the top plates or beams through direct bearing. Conventionally, The rafters are toe-nailed to the top plates using a minimum 3 16-penny box nails or 3 10-penny common nails or any one of the other two nailing patterns described in the fastening schedule provided in Section R602 of the IRC or Section 23410 of the IBC. While the code recognizes that these connections provide some wind uplift resistance, designers often supplement this by providing proprietary hurricane ties. For cases where rafters are supported on second-story walls, the rafters are typically supported on ledgers. This attachment requires careful engineering and detailing to prevent lateral separation between the low roof and the wall. Two possible failure modes includes the rafters pulling away from the ledger or the ledger and rafters assembly separating from the wall. The attachment of the ledger to the wall is typically engineered but may be conventionally framed if permitted by the authority having jurisdiction. The rafters are cut to shape at the upper end and supported on hangers with additional ties provided from the rafters to the wall studs to prevent lateral separation. Therefore, while shed roofs are structurally simple, their proper execution still demands skill and careful attention to loading and the continuity of the load path through each connection. The gable roof features two sloped roof planes that meet at a ridge, forming a triangular gable at each end. The gable roof is arguably the most common and emblematic residential roof type used in stick framing. It is loved for its straightforward geometry, architectural simplicity, and adaptability to vaulted ceilings or attic spaces. Gable roofs are popular not just for their structural clarity but also for their ease of construction and cultural symbolism. The gable roof shape is the iconic shape that generations in Western societies and beyond have instinctively associated with what a home should look like. In conventional framing, the ridge is a non-structural ridge board that simply provides a nailing and lateral bearing surface between opposing rafters without offering vertical support. The rafter pairs are tied together at their base with ceiling joists to form a triangle, providing structural stability through axial compression and tension. This creates a complete load path from ridge to wall with minimal need for added structural members. To understand how this system works, we need to understand a fundamental concept in engineering and physics known as static equilibrium. When a structure such as a roof is bearing on the wall as intended and is not collapsing or moving relative to the supports under loading, then we can say that it is stable. When a designer embarks on the design of a roof, the intent is that the roof will be stable under loading. However, stability is not always guaranteed in any system. Stability depends on the proper proportioning of roof members and connections to provide adequate load path that can guarantee static equilibrium. For a structure or object in static equilibrium, every push or pull on it is exactly counteracted by an opposite and equal force. If we consider a conventionally framed gable roof, we have vertical force acting on the structure. Static equilibrium demands that we have equal and opposite vertical reactions acting at the supports. Therefore, this is provided by the bearing walls at the ends. The stability of the entire assembly also depends on the stability of individual members that make up this roof system. Therefore, if we consider one rafter, we can see that the vertical force acting on it demands two vertical supports at each end to prevent the rafter from collapsing downwards. However, we know that in conventional framing, the ridge does not provide any vertical support. So the question is, how does the rafter maintain stability under loading? If we replace the rafter with a ladder and the ridge with a wall or beam, we can see that you can lean a ladder on a wall or beam as long as you provide adequate lateral resistance at the base to prevent the outward thrust. The wall or beam does not need to offer vertical support to the ladder. The only support needed is lateral support. As long as the wall does not move laterally, the ladder will not fall if the outward thrust at the base is resisted. This is what happens in conventional framing. The ridge acts as the wall and the rafter leans and presses on it. The ridge is laterally supported by the rafters and roof sheathing on the other side so it will not move laterally. This results in a horizontal reaction acting at the ridge towards the rafter that is pressing on the ridge. This force is resolved axially into the rafter and results in an outward thrust at the base of the rafter. For static equilibrium, this force must be balanced by an equal and opposite reaction. So how do we provide the required resistance to this outward thrust? If the wall supporting the rafter is a wood-framed wall, then it does not have the lateral stability to resist this force. Wood-framed walls are described in structural engineering as pin-connected at the base. This means that even though they are attached at the base, their resistance against out-of-plane rotation at the base is practically useless, which means that if pushed outwards at the top, they will rotate and not offer any meaningful resistance. Since the wall cannot resist the outward thrust, the solution lies elsewhere. The solution is provided by the ceiling joist, which is nailed to the rafter. By nailing the rafter to the ceiling joist, the force is transferred to the ceiling joist as a tension force. The ceiling joist must be continuous or adequately tied all the way to the rafter on the other end. This system is now in equilibrium under vertical forces. If you'd like to learn more about designing conventionally framed roofs, from sizing rafters and ceiling joists, nailing requirements, roof sheathing attachments requirements, and other roof framing requirements, then check out the Conventional Roof Framing Design course on our website at www.conventionalframing.com. This course is based on the conventional construction provisions in the International Residential Code and includes a final project where we take you through the design of a gable roof on a residential design project. What about uplift forces? Uplift forces are caused by differences in pressure between the interior and exterior of the building. If the interior pressures at the attic are higher than exterior pressures, the roof will be subject to uplift loads. For uplift forces, the code requires ties between opposing rafters or a collar tie to prevent the rafters from pulling away at the ridge. At the base of the rafters, uplift loads are typically resisted by the nailing attachment between the rafters and top plates, as we had described for shed roofs, and additional proprietary hurricane ties. It is important to note that according to Section R 802.4.4 of the 2024 International Residential Code, conventional framing of hip roofs is not permitted where the roof pitch is less than 312. In this case, the code requires the ridge to be designed as a beam. For cases where gable roofs are framed with ridge beams rather than ridge boards, the vertical loads from each rafter are resisted at the bearing wall and at the ridge. Ridge beams are designed to carry vertical loads and transfer them to posts that are designed to support this load. For gable roofs with ridge beams, we do not have the horizontal reaction at the ridge because the ridge beam is offering vertical support. We now have a vertical reaction at the ridge and at the base of the rafter, which satisfies equilibrium. Since there is no outward thrust at the base as we saw with conventional framing, there is no need to tie the rafter to continuous ceiling joists. Therefore, ceiling joists may be omitted, as is the case when framing vaulted ceilings. At the ridge, the rafters are typically attached to the ridge beam using proprietary hangers that are sized by licensed engineers or architects. The hangers are typically sized by a licensed engineer to provide both downward and uplift resistance that meets the demand loading. The rafter may also be notched to bear on the beam. In this case, the rafter will typically be nailed using conventional nailing according to the fastening schedule in the IRC or IBC, or the designer may provide proprietary shear connectors. These attachments are intended to prevent lateral displacement of the rafter and also provide uplift resistance. In most cases, uplift resistance is supplemented using hurricane ties from the rafter to the beam. The connection between the rafter and the top plate is typically similar to the connection that we described when discussing shed roofs, which is prescriptively described in the fastening schedules that are provided in the IRC and IBC codes. Having examined the load path on a conventional roof, which relies on ceiling joists to resist the outward thrust, we can see that any alterations to an existing house that result in cutting or removing ceiling joists should not be done without consulting a licensed design professional. If such ceiling joists are providing resistance against the lateral thrust at the base of the rafters, then the structure will fail under minimal loading. If the architectural design of the alteration to the existing design demands the removal of the conventionally framed ceiling joists, then a ridge beam or raised rafter ties or any other engineered solution must be provided. This is an example of the flexibility that stick framing offers when it comes to alterations on gable roofs. The hip roof is more geometrically complex and demands greater framing skill. It is framed by sloping all sides of the roof downward to the walls, with no vertical gable ends. The framing consists of a ridge board or beam at the top which does not extend to the end walls but is attached to hip rafters that extend diagonally from the ridge to each corner of the building. These hip rafters form the backbone of the roof's corners. Common rafters run perpendicular from the ridge to the exterior walls, while jack rafters fill in the triangular spaces running from the wall plate up to the hip rafter. For cases with intersecting roofs, rafters are framed from the ridge to a valley rafter. Framing a hip roof requires precise layout and cuts, particularly for the hip and jack rafters, due to their compound angles. Because of this, the design and construction of hip roofs typically demand more skill and careful planning than simple gable or shed roofs. As far as the conventional design of hip roofs is concerned, the 2024 International Residential Code specifies in Section R 802.4.3 that hip roofs at the ridge shall be supported by a brace to a bearing wall or be designed to carry and distribute the specific load at the point. This essentially means that the code requires either a post or brace supported by a bearing wall below or engineering analysis and design to ensure structural stability. Despite their geometric complexity and demand for highly skilled framers, hip roofs are still stick-framed in custom homes. However, the increasing availability and efficiency of prefabricated trusses is making them an attractive alternative, especially for builders seeking to reduce on-site labor or cannot find framers with the skills needed. Many other distinctive roof forms are simply adaptations or hybrids of the core three types that we have discussed. Clerestory roofs are essentially two shed roofs that are offset in height, joined by a vertical wall with windows. The wall may continue down to the foundations or include a beam where an open floor layout is desired. Dutch gable roofs blend a gable at the top of a hip roof. Gambrel roofs are a form of gable roof with two slopes on each side, creating more attic or loft space. Complex roofs, such as L-shaped buildings or cross gables, are often combinations of gable and hip segments intersecting at valleys and ridges. All these types may be stick-framed, although each variation introduces complexities that may require framers with additional skills and experience. As far as design is concerned, the complexities also introduce additional connection and support requirements which in most cases demand design according to accepted engineering practice. One particularly versatile stick framing technique that highlights this adaptability is overframing. Overframing involves constructing a secondary roof structure on top of an existing primary roof without altering its underlying framing. This technique allows builders to add features like false gables, shed extensions, dormers, or varying ridge heights that enhance architectural interest or function while maintaining the structural clarity of the base roof. Because the overframed elements are built independently of the main load-bearing system, they offer exceptional design flexibility, especially in custom homes where form and aesthetics are prioritized. In this way, overframing demonstrates the inherent flexibility of stick framing in its ability to go beyond basic structure to accommodate creative, layered, and highly customized roof designs. Having explored the various roof forms commonly framed using stick framing construction along with their structural properties, it's worth examining why this method continues to hold value in modern residential construction. Despite the growing popularity of manufactured trusses, stick framing offers a number of practical and architectural advantages that make it the preferred option in many situations. We will highlight 5 key benefits that underscore the continued relevance of stick-framed roofs today. First, stick framing allows for real-time decision-making and modifications during construction. Because individual rafters, joists, and hips are cut and installed on site, changes to roof pitch, overhangs, dormers, or intersecting roof lines can be accommodated with minimal disruption. This is especially valuable in remodels, additions, or when unforeseen conditions arise on site. In contrast, manufactured trusses must be ordered in advance and cannot easily accommodate last-minute design changes in the field without significant delay and cost. Secondly, stick framing supports a wide range of architectural outcomes that are often limited or impractical with prefabricated trusses. Designers can achieve vaulted ceilings or sloped interiors that follow the roof line and pitch, enhancing both spatial volume and aesthetic impact. Rafters can also be left exposed for a rustic or expressive architectural look, a feature not possible with the repetitive webbing of trusses. This flexibility makes stick framing especially appealing in high-end custom homes or projects where ceiling geometry is an integral part of the design language. While certain manufactured trusses, such as scissor trusses, can be designed to create vaulted ceilings, they typically offer less flexibility in ceiling shape and slope compared to stick framing. The geometry of scissor trusses typically results in a shallower ceiling pitch, thereby limiting custom interior detailing. Thirdly, unlike manufactured trusses, which typically fill the attic with diagonal webs that limit usable area, stick framing typically results in an open attic volume. This space can be utilized for mechanical systems, storage, or even finished living areas such as bonus rooms or sleeping lofts. In homes where square footage is limited or where future conversion is anticipated, this functional attic space becomes a significant advantage of rafter-based roof construction. Fourth, stick framing relies on readily available dimensional lumber that can be sourced from any local lumberyard. This reduces lead times, simplifies delivery coordination, and avoids the scheduling complexities associated with truss manufacturing and delivery. In remote areas or small projects with tight timelines, this logistical simplicity can be critical. Ordering manufactured trusses from distant locations can be time-consuming and may introduce unnecessary logistical complexities. Finally, while stick framing is often more labor-intensive than using prefabricated trusses for large projects, there are situations where it can offer cost advantages. For example, in remote or rural areas where access to truss manufacturing plants is limited, the transportation and delivery costs for prefabricated trusses can be significant. In such cases, sourcing dimensional lumber locally and framing the roof on site may be more economical. Additionally, when the roof design is simple and falls within the limits of conventional construction outlined in the International Residential Code, designers and builders can avoid the added cost of engineering required for trusses. Stick framing also eliminates the need for crane rentals in many cases, further reducing project expenses. While not universally cheaper, stick framing can be a more cost-effective option under the right circumstances, especially for modest-sized projects or sites with logistical challenges or for cases where the homeowner is also the builder. If you have enjoyed this video, please don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.